So for this afternoon's keynote, I'm very pleased to be able to introduce our next speaker, Finale Doshi-Velez. She is an assistant professor of computer science at Harvard University. She is excited about methods to turn data into actionable knowledge, and her core research is in machine learning, computational statistics, and data science, which is often applied to the objective of accelerating scientific progress and practical impact in healthcare and other domains. We are very excited to have her with us here today to talk about reinforcement learning for optimizing healthcare decisions. So over to Finale. Thank you.
Hello, everyone. It's been such an awesome week. Usually I come to a conference and by the end I'm totally exhausted and I'm still energized. I've had so many great conversations and it's such a great pleasure to be here today. So what I'm going to be talking about for the next hour or so, 45 minutes, is talking about some of our work in terms of how to improve healthcare decision-making using machine learning and specifically reinforcement learning. And before I do that, I want to just start out sharing a little bit about myself. So I started out as an aerospace engineer, actually. That was my undergraduate degree. And I still feel like that was a very useful skill for me, even though I no longer work in that field, because there we were taught that if teams don't work together, the plane falls out of the sky. And I think it's a very important piece of information to remember, especially in this age of like we're building and trying to deploy AIs, that these are complicated machines, and we want to make sure we deploy them responsibly. From there, I decided I was more interested in the robots than the space part, so I became a roboticist. I worked with a robotic wheelchair. This is me and a robot. Like I modded a wheelchair and took out all the guts, and we put in new wires, and it was fantastic. But as I was going through this, I was like, well, the thing that I really like about all this is not the soldering and the magic smoke that comes out of the machine when you solder it incorrectly, but I really love the math. So then I took a little bit of break from robots, did something with no applications whatsoever, spent 2 years learning about Bayesian nonparametric statistics, and then finally found this middle ground toward the end of my PhD working in reinforcement learning, where I was using statistics to help make decisions. At the end of my PhD, I realized that I loved what I was doing, right? And what you'll take away from this talk are like how these methods can be really useful in a lot of applications, and how I also just think that the math is really beautiful. But I realized also that I couldn't just be happy doing beautiful math, which brings me to what I've been focusing on for the last 6 or so years, which is how can we use machine learning to help with healthcare decisions. And we're doing work in intensive care units, we're doing work with HIV management and depression treatment optimization. And in all of these cases, people give us their data and are looking to see how can we help them improve the treatment decisions that they're making. And the big theme is that we have to recommend decisions with a lot of uncertainty, right? Unlike Atari games or chess or these sorts of games, when a patient comes into the clinic, we take some measurements, but we don't know all the things that are going inside their bodies that may be affecting their health. We don't know necessarily all the things that are going on in their environment that may be affecting their health. So we get a very narrow view of the patient, and from that narrow view, our goal is to help make better decisions. So that's the theme that kind of actually wraps through a bunch of work that I did in the past. And I want to share this initial story also in part because, my path was not linear. I didn't go to college being like, yes, this is machine learning for healthcare. This is what I'm going to do with my life. So all of you, as I've been chatting with over the course of the week, also have had many nonlinear journeys, and that is totally great and fine. And all the skills that you build from each of those steps are going to be really valuable along the way. All right, so let's get to today's focus. So how can reinforcement learning specifically help with treatment decisions, right? So I'm going to be focusing on individual patients. So here's the basic reinforcement learning paradigm. We have some agents, we have the world, and then the world is a black box, right? We don't know what's going on inside the world. This could be going on inside the patient. But it's sending us observations, measurements, for example, about how the patient's blood pressure is looking, and also rewards. And then there's kind of two important pieces that are going on inside the agent. There's some notion of like, what does the patient look like right now, which you're going to call the state. And then there's some notion of like, how might the patient's state change if I took a particular action, right? This ability to think about the future. And this is the model, right? And if you're not doing model-based RL, there's still this notion of like futures that are possible. And then based on these two things, the agent has to spit out an action and it goes back into the world. And the reason I emphasize this version of the picture is, again, we can build all sorts of models of what we think might be going on inside the patient, but we don't actually know. All right, so how might we actually solve this problem? So I'm going to ground this problem in some work that we've done in HIV management. So one thing you could do is actually build that model, right? So here's like a cartoon. We can make that more specific. We could say that there's some hidden state of the patient that we don't observe. And depending on that hidden state of the patient, we're going to get different types of measurements, like different types of CD4s, different types of viral loads, different types of mutations of the virus. So these are things we can measure, and it all depends on the internal of the patient. And then the drugs that we give for treatment are going to affect how the patient's internal state changes. So we can set this up. This is a PUMDP, and we can try to solve this. And various people have tried to solve this sort of problem, including people in this room. And so, the trickiest part about this, if we set up the problem like this, is how do you get this model right? You got some data, and now I need to fit a function of like what's going to happen to the patient in the future given the patient's measurements now. Right, and especially these are not really large data sets, right? In my eyes, these are large data sets. We have like data set registries with like 30,000 patients. So to me, this is a fairly large data set. But from a deep learning standpoint, this is not a large data set, right? And so fitting this thing is hard, and your model could be wrong and biased in all sorts of ways. Well, what's the alternative? Well, one thing you could do is just look for similar patients. So there's another line of work that says that here is all the information that I have about their patients. I have their trajectory of what for example, their CD4 counts have been in the past. And given that, and maybe information about mutations, I'm going to try to find a similar patient in the data set, right? So if I'm this patient over here, I'm going to try to find that other patient who's kind of looks similar to this patient. And then I'm just going to guess based on what that patient's outcomes were. Right? And the advantage of this is, in this case, I was trying to fit some crazy function. In this case, I don't need to do that anymore. I just need to find a similar patient. And the core insight that we had when we were looking at this is that these two notions, these two views that I've just shown you, are complementary to each other. And they're complementary in the following sense. So let's say that this is your group of patients. This is a cartoon, but it captures some realistic things that go on when you're looking at healthcare data. Namely, there's some groups of patients that actually cluster together, right? And your disease may look very much like the disease of several other people. In that case, you are very lucky, right? Because you have your version of the disease looks like versions that we've seen in the past. And if that's the case, we don't need to build any fancy models, because if this is you over here, we just look at people who had a similar version of the disease and see who had the better outcomes and which treatments did we give those people that led to the better outcomes, right? So this is kind of a scenario that you want to be in, if possible. However, it might not always be the case that you're lucky, you're in the cluster. And actually, not with HIV specifically, but if you look at rare diseases versus common diseases overall in health, rare diseases make up about 10% of all diseases, right? So there's like thousands of rare diseases, but together they're actually quite common. So it's quite, and that's just to say that it is quite common. It can be quite common that you get unlucky and you don't have a neighbor that had the same sort of disease behavior that you did. So if you're sitting right here, our insight was that it may not be the best thing to map to the nearest person, maybe this one or that one or that one, because they really look nothing like you, right? And it may be better to fall back on a simplified model-based approach that uses some form of function approximation. It's not going to be perfect, but underfitting or using a simplified model of how your disease was going to progress might be better than assuming that you look like someone who really doesn't look like you at all. So that's how, these approaches are kind of complementary. Depending on the type of patient you are, you may want to use one or the other. So we took this idea and we put them together in a fairly straightforward manner. So the kernel is find a neighbor. The POMDP is use a model. Each one of these agents, you can imagine, suggests an action, right? The model selects an action, and then you try to find your nearest neighbors, and that suggests a treatment decision. And then you put in some statistics about the patient, and now we have this function here, which is just going to pick between the two choices, right? Those two choices that I highlighted on the previous two slides. So either the neighbor or the model. Both of them are going to suggest an action, and we're going to try to figure out which would be the best for the specific person automatically without having to like a human to have to take a look at those two options. So so that's the main idea. Now let's go to the application that we did. So we looked at around, as I said, around 33,000 patients from the EU Resist database, and we have their observations. Don't include just the standard sort of things like CD4s and viral loads, but also this particular cohort gets the virus genes sequenced every 6 months, so we can see mutations happening along the way. And the action space, I just want to point out, is quite large because we're looking at all the common cocktails that occurred in the data set. So there's over 300 actions that were taken. Actually, before I go any further, I just want to credit, so this work was done with Sonali Parbo, who is from South Africa, and has just joined my lab as a postdoc, and this is work that she did during her PhD with me. Worked together during her PhD at Basel with me at Harvard. So we apply this general approach, and we see that our intuition kind of makes sense in terms of the numbers. So in that first slide that I showed at the beginning, I had this kind of weird-looking reward function, which came out of discussion with the clinicians. And I'll come back at the end or toward a little bit later in the talk to talk about what it means to choose like a funky reward function, right? It's a very important question. But for now, we chose some reward function that involved, keeping the viral load low over a long period of time, which kind of implicitly also means that you don't want to collect too many mutations along the way. So here are different policies that we considered. So do you only look at neighbors, or do you only look at models? And what you see is that if you only look at neighbors, that does quite a bit better than only using a model. And the reason for that is that many patients have similar patients to them in the data set. And also, modeling the progression of HIV is complicated, right? And so fitting this model is actually super hard and gets a lower performance than just looking at neighbors. But if we combine them in the approach that I pointed out over here, where you get to choose for a particular patient which choice do you want to make, then our performance is even better than the model alone. That means like using the model for those patients who don't really have any buddies is beneficial. And we can get a small additional boost by incorporating this idea of looking at neighbors, not at the policy level, but at the model level. And what I mean by that is the following. So over here, we're trying to figure out what's going to happen when we take a certain action in orange to the patient state in yellow. And really, there's kind of two ways to imagine how that might happen, right? We could, again, have fit like our deep network or a POMDP, like parametric model, and it says that, like when you have this action and this state, the next state is given by something, right? So the output of your deep network. Or we could say, well, actually, if you were in this state or this history and you took this action, well, let me go into the data set and let me find other patients who had a similar history and took a similar action, and let me guess their next observations just based on data that I just have in the data set. It stays very grounded with the data. So I have these two options, and maybe I can mix between these two options. So if I'm lucky and my history until now looks like a lot of other people's histories, then maybe I can use that information when predicting my future, because I look at what happened to people in the past. But again, if I'm unlucky and I need to predict the future and I don't have anyone nearby, then again, I stick it into my model. So if we do that, that's the last thing on this slide, we get a small additional boost in performance, right? So this is showing that this notion of mixtures is really powerful, and in particular, this mixture of this non-parametric model looking to the data versus some sort of parametric model it's a very useful trade-off between those two benefits. And if we look at kind of like this, I've been like hand-waving through literally why you might want to choose between one model and one model, but it does actually happen in the data. So if we look at the distances, actually let's start with this plot, between neighbors. The kernel policy, the neighbor, find a buddy, find a neighbor policy, is chosen more often when the distance is small. And the POMDP policy is chosen more often when the distances are large, right? You have no buddies, so you have to fall back onto a model. And this typically happens when the histories are long. Because if you have a relatively short history, like you want to make recommendations for a patient, only after a couple of visits, it's quite likely somebody else has a couple of visits just like that. But the longer that patient has been in the healthcare system, the less likely they're going to match exactly or very closely with someone else. So this all was kind of just a sanity check that it all looked like it made sense. So then we celebrated, right? I mean, hey, those look like great numbers. Let's go solve some other problems. I'll come back to whether we should have been celebrating. Let's go solve some other problems. And so we said, maybe the same idea, we applied it to HIV management initially, can also be applied to other problems in which we have to make multiple treatment decisions about a patient, and decisions that you make now may have long-term effects in the future. Specifically, we started looking at critical care units, or ICUs. So in this case, if you, for example, you put a patient on a ventilator, you lose certain options about what sort of things that you can do with them in future. If you're trying to manage their blood pressure, different drugs have different trade-offs. Some things are safer but not as effective. Other ones are effective but may also cause the person to go into shock. And so you want to kind of be careful in terms of how you choose. These are hard decisions, and the intensivists, came to us and they said, we don't know how to make these choices. So specifically, we looked at this cohort of about 15,000 patients with sepsis, which is a full-body infection, in the MIMIC data set. And it has vitals and some lab tests. And we focused specifically on this question of blood pressure circulation management, where there's basically two types of choices. There's vasopressors, which constrict the blood vessel, and therefore increase blood pressure and kind of force things to keep moving, or fluids. So if you add more fluid into the body, that also kind of pushes things along by increasing the blood pressure. So you kind of have these two options, but they have very different trade-offs. And then we said our goal is to reduce 30-day mortality, and we set up our rewards based on the probability of 30-day mortality. Don't worry about the exact function for the moment, but just this notion of the probability of future mortality. And the reason we did that is that mortality is a very far away outcome, right? We make many, many decisions before we find out whether the patient made it or not. And for reinforcement learning, this makes it a very challenging problem, so we simplified it a bit by saying that how is the probability of mortality changing over time? And if it's going down, then we're doing better. And we made a few changes, but roughly the same idea holds from the last time. So there is still this notion of a kernel, right? Find your buddy in the data set and recommend the actions that worked best for people who are similar than you. And then a couple of things that we changed is our work with HIV. We were using very traditional POMDP models. Here we used an LSTM and a DDQN to deal with the slightly larger dimensionality of all the spaces. And then we also have patient statistics, again, going into actual action. One other thing that I'll point out is that we noticed in this particular case that sometimes the agent was making completely wacky recommendations. So we added this guardrail, which basically said, the model's never allowed to recommend an action that was rarely taken in practice, right? And so for all of you who are thinking about reinforcement learning for the real world, these sorts of details are really important because especially when you're using function approximation and deep models, you get to some part of state space, who knows how that little part of state space was trained, and it could be recommending completely wacky stuff. All right, so then we applied it, and so this is the score that the clinicians would have gotten. This is the score if you use the kernel only, find your neighbors. This is the score if you use the DDQN or based method only. And this is a score that you would have gotten if you used our approach, the mixture of experts. With these methods require setting certain covariates for the off-policy evaluation, so for 2 different choices of covariates. And specifically, the difference between these 2 options is, do you believe that the patient's measurements right now are sufficient for everything in the thinking about the future, which is clearly not true. What happened to them before this particular hour is important, or do you consider the whole history? And what you notice is especially as you're including the whole history, these numbers here are quite a bit bigger than those numbers there, right? So again, that's looking good. And just to visualize what's going on, we looked at the following visualization. So here on the x-axis, I'm showing you the difference between what we recommended and what was actually done. So 0 means that the clinician did what we would have recommended on both of these axes. And then the side plot here is the mortality rate for that population. So imagine going to all the patients where the difference between our recommendation and the clinician recommendation was small, and measuring their mortality rate in that group, and we see it's quite small. And then we go far away, right? And we say, when did the clinician do something really different than what I would have recommended? And if we did something very different, what's the mortality rate? And what you see is the mortality rate goes up when the clinicians deviated from our recommendation. So I'm going to pause for a moment, kind of like, does this make sense? Show of hands, nod heads. Okay, yeah, this seem reasonable? Maybe some people are raising their hands. Yes, okay. All right. So we also were kind of happy when we saw this plot. We were like, oh, this is kind of another visualization that things are going well. And then I had a couple of students do something that nobody would necessarily do in RL, but they were just playing around and seeing like, okay, I'm just trying to get my code to work. And they're like, what happens if I plot a random policy on this curve? Clearly that's a bad idea, right? Treating patients with a random set of treatments is a bad idea. What happens if I plot the no action policy? Never take an action on this plot, right? And we know, again, that this is a bad idea, right? The patients are in the ICU. They probably need some treatment, right? These are patients we selected. We know that they needed some sort of hypotension treatment, right? And what you see is that there's no difference between this, or basically no difference between these 2 policies, which are clearly bad, and a policy that we believe is good, right, on this plot, which is very weird, right? You guys should be like, this is odd. And the reason this happens is because most of the time, patients get no action, right? Like if you imagine that a patient is in the ICU for, say, 100 hours, the number of times that an action is actually taken is relatively small. And in fact, the finer you bin time, the smaller the fraction of the time that actions are taken, right? It kind of makes sense, right? If you did 5 actions to this patient during their stay, the finer you bin time and stuff like that, the smaller the percentage will be. So many times the correct action is no action. Many times, the doctor does nothing. We recommend doing nothing. And you get a difference of 0, and those are the healthier times, right? The times where you're not really actively working on the patient, or patients that get no action whatsoever. They're the patients who are doing all right, They're in the ICU, but they're doing better than the patients where you're frantically trying to do something to make them better. So overall, this is not just a 0 difference, this is just 0 action. And of course, you expect 0 action to have better survival rates. So anyway, if that was too technical, the key point that I want people to take away from here is that this was weird, right? Like this was an unexpected plot. And really, if we had not happened to run this, right, and we had just gone forward and said, okay, we have found a way to treat your patients better, improve outcomes in the ICU, we could have done a lot of harm without meaning to, because really we had no clue, right? Or at least based on these numbers. I hope to show you in later parts of the presentation that we do have some clue, but from here, you couldn't have told. And the reason why I want to pause there is that, this week there have been a number of discussions around the ethics of AI, and making sure that we respect people's privacy, that we are respectful of different sorts of cultural norms and values and discrimination and bias and fairness and all of these other things, which I'll get to and are very important. But I also want us to make sure that we don't forget that we can screw up without meaning to, right? This is just engineering professionalism. You build something, you don't build it to the right spec. It's not about harm due to kind of a moral harm, like a fairness type of harm. This is just a harm of sloppy work, potentially, right? And I just want us to remember that, because especially when we're using our function approximators, who knows how they exactly get optimized, what local optima they end up in, what sort of numbers they're spitting out, especially even with small deviations from the current point that you've evaluated at. But all right, okay, so this caused us to do some very careful thinking about how can we increase the confidence in our results. So here we have this the system that I built for you, and there's actually a lot that's happening that's not actually part of like that agent world system, right? Somewhere along the way, we had to specify a reward function. We had to choose a representation or a state space. And then after we do this work, we have to kind of choose how we validate. And at this point, I'm actually going to pause and mention that we don't experiment on real patients. That's probably obvious. But our setting involves the following. We go to a hospital. They give us a bunch of data. And once we get that data from the hospital, we look at that off policy. We look at that data off policy, right? We're trying to make recommendations based on batches of data. So then after the whole, this loop over here, which I'm going to call like the optimization loop, right? This is the part where we're trying to find the best policy. We still have to figure out how to evaluate it. And so this morning, I talked about some of the work that we're doing in our group having to do with off-policy evaluation, which is statistical methods to try to estimate the quality of a policy. And for this afternoon, I'm just going to mention that you reach like some hard statistical limits very quickly here, partly because at some point, the variances become too big, right? You can't tell just by the data set that you have whether some policy is better or worse than another policy. So this is a very interesting and active area, but it's going to have some fundamental limitations. So the next thing is like, how can you do additional checking to make sure that whatever recommendations that you're giving are responsible? And so that's what I'm going to spend the next half of the talk talking about, right? So focusing on the checks. So the first thing that we did, so I presented this kind of in a funny order just to illustrate a point, right? So in practice, we didn't just, run a bunch of numbers on like our HIV cohort and say, okay, now we're done. We have solved the problem of AIDS and we're moving on. We did a lot of checking to look at the reasonableness of the policies, and now I'm going to expose all of that homework that we did because that's all super important, as I just pointed out. The numbers can often lead you astray or just, not be able to distinguish between certain policies. So what sort of homework did we do? Well, the first thing that we did is we tested whether our results hold across multiple cohorts. It's always a smart thing to do. So when we look at data, I think in this case, actually, we trained on the Swiss HIV cohort, and then we take the same policy that's learned there, we apply it to the EU resist cohort. we get similar properties. And these populations are not super different. So you would hope that if there was just some weirdness in how the data were collected and there's some bias, that happens all the time, that one group decides to collect data in one way and another group decides to collect data in another way, you would hope that it kind of shows up here. But the similarity suggests, again, that gives us some confidence that things are better. And just as an aside, Sonali, who just joined our lab, did her bachelor's and master's in Johannesburg and working with HIV data there. And what we're trying to do now is see whether the recommendations that come out of here on a very well-managed and well-curated cohort can be used to boost recommendations in a cohort where you don't have this every 6 months get all your viral genome sequenced type of population, which would be super cool to be able to transfer across those domains. Another piece of things that we did, and again, you don't need to understand all the plots, they're just there to show lots of homework, but there's lots of parameters that go into all of our estimation. And we check the sensitivity of our policies and our off-policy results to those sorts of parameters. So here, for example, the off-policy evaluation methods take in a number. It takes in your guess of how well you think the policy is going to do, and that's a variance reduction technique. But that means there's an additional parameter. There's this number this guess that you have to make. And depending on the guess, you will get different values. And what we did here is saying that if we vary the ways that we do our guessing, does it still look like our policy is better than the clinician policy more often than not? Because you hope so, right? So this is another bit of homework that we did. All right, so and I could give a long list, but I'm just giving you some examples of homework, especially if you are in the RL space that you should be thinking about. All right, so now you've finished kind of, at this point, I feel like we've reached the end of what statistics, machine learning, AI, data scientists can do on their own, right? Kind of in terms of how much can you do, and I think it is your responsibility, it is our responsibility to do as much as we can to validate our results before we show them to clinicians, right? Because their time is very valuable, and the more we can prune out bad options without their input, the better. But now, let's suppose that we've done all of that, and we reach a point where we still, we still don't know whether this policy is a good idea or not, right? So this is now some work that we're doing with the mind of working with clinicians to help us evaluate whether these ideas that we get from looking at these batches of data are reasonable. All right, so this is work in progress. I'm just going to talk about it very briefly. But one thing that we are very actively working on is, let's suppose that initially there's many policy options, right? Like you're trying to go from some start to some goal. All the black lines represent potential options. Some of them don't even reach the goal, right? So if you did all of your statistical off-policy validation, all your homework, everything you could do, maybe you could remove some of these options as clearly faulty options. Let's say that you can remove the ones that don't reach the goal, right? That might be fairly easy to detect. And then you can also maybe remove one that seems to just take a very circuitous route for no reason, go past the goal for no reason. And then you still have some options left. I would argue that it actually, in terms of hubris and humility, the humble thing to do is to provide the options, right? You don't want to go in and say, I have found the solution for you. You want to say, I have a menu of solutions that all seem quite reasonable. And then with your expertise, maybe we can decide whether they are truly all reasonable, or maybe some of them are bad ideas and we just couldn't tell from the data that we had collected. And this is really relevant in all the domains, but the place where we're applying it or thinking about applying it first is actually in the domain of mental health, where we can suggest drugs that will probably work for your depression, drugs that will probably not work for your depression. But amongst the drugs that will probably work, there's going to be some very personal decisions that have to be made, right? Like, do you want to be fat or do you want to not sleep? All these drugs have side effects. You have to pick your poison, right? And you don't want a machine learning system making that decision for someone. So giving people choices amongst options that you think are all reasonable is actually super important. And more broadly, all of the collaborations that we do, we don't just download the data sets and crunch numbers on them, but we have conversations with the clinicians. All of my students, for example, have rounded in the ICU and just watched the care teams caring for patients, and just seeing the chaos of it. Actually, going in there kind of makes you be like, okay, I never want to end up in a critical care unit, and also just emphasizes the need for systems to help them manage the flow of all that information. So specifically, what are things that we're doing to include the experts? Well, one work that we've already done in the case of HIV is we've checked against the standard of care, which is a form of expert knowledge. But we also did a survey with 3 clinicians where we gave them the data about the patient and the recommendation. We asked them whether they would agree or disagree with the recommendation. And what you see is that for most part, they seem to agree. And also, when they disagree, the disagrees didn't match across clinicians. So the 2 cases where the clinician was like, well, I would do something slightly different, are not the same as those 4 cases, right? So kind of our algorithms were in the noise of the inter-annotator agreement, right? That to the extent that clinicians already disagree in the options, our algorithms were kind of in there. So that made us feel better about our current recommendations, and that's kind of ongoing work that we're hoping to publish soon. All right, but this raises a question of, well, what's exactly the best way to ask the doctors, right? And this is quite tricky because in this particular case, we just gave them 30 examples, and we said for each of these 30 examples, was the system good or not? And that's a little tricky because that puts a lot of responsibility on us, right? Because now we had to pick somehow 30 examples that were representative of what our system was doing, and maybe instead of having them annotate each decision, wouldn't it have been great if they could say, overall, I think your system is pretty good, but it doses too high in certain situations, or doses too low in certain situations. I would tweak that part, but keep the rest the same. Which is a theme that I'm going to come back to, right? Like, how can clinicians work with your AI system to get to better decisions than either alone? So that led us down this detour of how do you summarize a treatment policy, right? Because we're using these LSTMs, we're using all sorts of complicated temporal models. Like, how do you even tell someone, well, this is roughly the treatment policy? It's very tricky. So we formalized that problem, and this is a great example of how, when you work with the real-world problems, you get all sorts of interesting research questions that you wouldn't have necessarily dove down before, and now this is very fascinating. So here we come up with the following game. So we get to present the expert with some state action pairs, right? So this is like saying that if the patient looks like this, then we take this action, right? So that's what we give to the expert. And then the expert has to predict what action the agent will take, not the right action, just what action the agent will take in some new state. And what this is testing is that if I've done a good job of picking some good examples, then hopefully the human, can generalize from that and say, oh, this is an aggressive driver agent. This is a very conservative driver patient or agent. Sorry. And our goal then is to choose these state action pairs so the expert can do the best job of predicting how the agent will behave in a new situation. And this is also just an important thing for trust, right? That you don't want, the expert doesn't want to be surprised by what the agent is going to do. So here are 2 examples of setups of this problem. Let's suppose I gave you a grid that looks like this, and these arrows are examples of state action pairs. So these are the actions that the agent took in each of these states, and a dot means no motion, right? So if you look at that for a little bit, can anyone have thoughts on what the agent's trying to do? Okay, some people are like, go to the middle. Any other hypotheses? Louder? I can't hear anyone. This is just confused. You can raise your hand if this is it, no idea. Okay, that's fair. And the rest of you have ideas, you're just not telling. That's fine. All right. So when people look at this was our study, right, to see how they're going to respond. And specifically, we would give them things that weren't labeled, right, like this one, and say, what do you think the agent's going to do in that situation? And maybe you can kind of tell that the blue dots are only on the round circles are only on the blue dots. And that the round circle, as I said, meant stop. So the agent only seems to stop on the blue dots. So it seems like maybe the blue dots are valuable, right? Maybe? Okay. All right. So now I give you another example. So this is out of a very, very baby, I should emphasize, HIV simulator. And I'm giving you some treatment trajectories. So like treatment B, treatment B, treatment B. And this is how the variables change for that particular patient. And I give you a couple of examples. And then I say, now, what's the agent going to do if they come in and the patient's statistics look like the following, right? So how many people find this a harder problem than the previous? Yeah, some people? Okay. Most people did when we did our survey. And this is also just pointing out, like, this problem looks very different than this problem to most people. And here, at least, it's like, at least when I look at this, I can't figure out what the goal is, right? I can't figure out what's the equivalent of, like, the blue square. And I'm like an RL person, right? Like, I should be able to look at this and know, but I can't. So then what we did is we gave people surveys. And the reason, by the way, that we simplified all this down to these sort of, non-clinical domains is that we wanted to really be able to study this question and get repetitions and stuff. And getting lots of reps with doctors is hard, right? It's hard to get, hundreds of doctors to take your survey and stuff like this. And in this case, we wanted to be able to run this like on Mechanical Turk in a large study and be able to understand, how do people generalize given a few examples, if this is our strategy for presenting an agent's policy. And what we found in our studies is that with the HIV simulator, people tended to, and IL stands for imitation learning, IRL stands for inverse reinforcement learning, and the way you can think about it is copying versus finding goals. So for most part, they had also no idea what the goal was in this particular situation. And so when presented with, when presented with what would happen in this state, they just looked for something in all of the data that looked kind of like this picture, maybe this one over here, and said, oh, okay, like this one kind of looks like this one, and they did treatment B, so my guess is B. So that's what this tall line on imitation learning means. Just find something and copy it, right? This is coming back to that theme, this recurring theme of like finding a neighbor versus building a model. So people, when they could not really understand the domain because it looked very abstract, they just tend to find a copy, right? It's the easiest thing to do. And then in the grid world, it depended. And the non-specific, we asked people to fill this out on a form, right? So non-specific means that you couldn't, their description on the form didn't match either of them, which is important, right? People are thinking about this problem in ways that we didn't expect. But between copying and goal finding, more people thought that, oh, I think the agent's trying to get somewhere. It's trying to get to that blue square. And then what we find is that if we guessed right, so if we guessed that the human would use a copying approach versus if we guessed that the human would assume that there's some goal that the agent has, that affected the performance. So the dashed lines show the predictions computationally, and then the bar charts show the actual performance. And what we see is that in the HIV domain, for example, if you use like the IRL extractor, we kind of expect it to do worse. We expect the human to be able to get to here versus here. And we see, again, that it's slower. So it's important to account for this, right? That's the key point that we're trying to make here, that if you guess wrong, so if you build a summary, assuming that the person's going to be able to extract the goal from it, but they can't, right? It's like too complicated. And instead, they're just copying. Then you gave them the wrong type of summary, and you're going to take a hit in performance, of like how well the human is going to be able to understand the agent. And you want to make the human understand the agent. So it's important to get that your mental model of the human right when you're extracting that summary. All right, so now I want to step back a little bit, right? So and really think about how all these pieces fit together. So for most part, we've started out with, again, I get a batch of data from the hospital, and like the agent was trying to produce a treatment policy. And of course, that's not really what happens in practice, right? Because as I was saying, for a variety of reasons, we don't collect all the data that we need to be able to make a healthcare decision based on the agent alone. And for the foreseeable future, I don't see that changing for most domains. And so really what we should be thinking about is that what information can the agent provide to the final decision maker, the doctor, to make the right choice about the patient. And I put Spider-Man on the slide because there's no code for bitten by radioactive spider, something only his doctor can know. It's not going to show up anywhere in the data set, but it may be important to know when you're treating, right? And I think this is really how we should be thinking about our treatments and policies. There's been a theme throughout the week where people have been talking about, I don't have a lot of data, or I'm missing a lot of key information. Can I still do reinforcement learning? Can I still use AI? And this is the question I would ask, right? Like, is there something in the data that if it were exposed could help a decision maker, which might not be the agent, make a better decision? And if that's the case, I would say that not only is the answer yes, but in something like healthcare, we kind of have an ethical responsibility to try to improve, help clinicians improve their decision making, right? If being able to search through all of this data can help with the final decision, that's a really important thing to be doing. All right, so kind of related to that though, actually. So this is a case where it can make a difference. I want to point out kind of two distinct cases of like when AI is needed and when it's not, right? Because we're all here, we're very excited about AI. So like, this is like the case where I would say, yes, you should use something. But I really want to contrast. This picture is from Makerere University. There's been a bunch of cool posters along similar lines of can we use, for example, smartphones to help with pathology, radiology, all this sort of stuff, right? This is fantastic because, it's filling a real need that couldn't be solved any other way without AI, right? There's just not enough pathologists to read the slides, and there isn't some other simple tool that's going to be able to do the image analysis for us. And I want to contrast that with something like a community health worker flowchart of when to send someone where for treatment of malaria. This is a very simple chart. It can either be given to someone or just expert coded onto an app on a phone or via SMS. And it doesn't require any sort of additional intelligence whatsoever. And I point that out because if there is a simple solution, you probably want to go for it. Another theme that we've been talking about in various conversations over the week is okay, there's things that require no AI, and there's things that require prediction, and at some point you get to things that require reinforcement learning. And make sure that you're really thinking about, does this problem really need this? Because as I pointed out earlier in the talk, so many things can go wrong when you use AI for some application. We want to be really careful, and if there's a more robust solution, we should use it, right? There's when I was in my undergrad doing aerospace engineering, they always told us a story about how the Russians used pencils to write in space, whereas in the U.S. they invented ballpoint pens to be able to solve the writing problem, right? And it's there was a very simple solution that existed that probably could have been used. All right. So going forward, right, so I'm going to zoom out a bit now and talk much more generally than the specific stuff about reinforcement learning for healthcare. I started out, telling you a little bit about my journey, emphasizing the fact that it was nonlinear. And for me, the challenge for a lot of my kind of high school, college life was trying to figure out, I'm a math nerd, right? I really love working with probability and statistics. I was telling someone earlier, like I saw a particle filter in importance sampling for the first time, and that was like love at first sight. I was like, this is the coolest thing. I have to work on this because it's just so much fun, right? And so that was clearly the passion, right? And then it took me a while to figure out how to connect it to the impact that I wanted to make. And so for all of you in this room, I think this is a really important question to be considering. I mean, you're here because you love AI in one form or another, but as I just pointed out earlier, there's a lot of problems that can be solved very well without AI, right? And so really just, if you really just want to solve that problem, maybe you want to think carefully about whether AI is the right solution, solve the problem in the best way it can be solved. But if you have this tension, right, where you want to do some good, but you also have a particular thing that you just love doing, in my case, reinforcement learning and probabilistic modeling, it may take some work, but you can find ways to connect it to the impact, and that's okay, because we need a large, diverse ecosystem of innovation. Some of it's going to have fruit in the short term, some of it's going to have fruit in the long term, and if we don't diversify, we'll miss out on potential options, right? So it's just as important to have people thinking 15 years down the road as it is to have people thinking about tomorrow. And then another thing that we've been hearing about on the week, but I just want to really emphasize it again, is that once you've done that, right, you kind of figure out what you want to do, you want to monitor and course correct, right? Because I've been emphasizing over and over, here's how we could have screwed up, right? And, we won't know until the final, we're thinking about how to roll out silent trials where the patient won't actually be affected, but we're going to test all the IT around how a system would actually work to make sure there's no bugs there, et cetera, et cetera. We have a plan on how to responsibly roll out some of these systems, and we will almost certainly get something wrong, right? And it would be bad not to try to accept the status quo because we can't make any mistakes, right? We don't want perfect to be the enemy of the good, but at the same time, it would be wrong to not be watching for mistakes and correct them. So again, for those of you who are thinking about creating startups and businesses around AI, I think the most important thing we can do is surveil ourselves and monitor our systems and look for weirdnesses as we start deploying, because we're not going to be able to find it necessarily earlier. And then the last thing that I want to mention is that all of this in our professional sphere has an analog, I believe, in the civic sphere. And it's important not to forget that as well. One thing that AI is forcing us to do is articulate our needs and values, especially our values, right? Because an AI system takes in a reward function and it applies it to everyone, right? Or you have to design it maybe to not apply it to everyone or apply it differently to different people if they might have different preferences. But it's going to do whatever you tell it to do. And it's going to do it across the board. And so if we have, for example, in the U.S., we have, law around anti-discrimination. But, what is that in math, right? Because the system only understands math. And what this is really forcing us to do is figure out what our values are. And I feel like us in this room, we understand that tension, right? We are experts at explaining how different choices around different functions, for example, like fairness, could have very different effects on how the system behaves. So I really think that we have a responsibility to engage with policymakers to help educate them on how the different choices what's the menu of options and what are the effects of all our choices. Because no one outside the AI sphere is more expert than the people inside it in terms of how that translation has to be done, right? We understand that everything has to turn into some Python code or some equations and the limitations of that. And the other piece in terms of monitoring, course correcting, kind of the analog I feel like in the civic sphere is, just because you're building a tool to solve a problem now or in a particular domain, doesn't mean that you should ignore the larger problems. I think it's kind of a responsibility. Like when I'm working in the healthcare space, I'm always aware of the fact that in the U.S. the incentive structure is completely wrong. right? And it's not my main focus to correct that incentive structure, but I do think about it, and when I have the opportunity to advocate for other forms of incentive structures, I do so, right? Because I think that I can't just walk into a domain and just be like, I'm going to be your math person. I'm not going to really care about the whole of your problem, right? If you're working in the education sector, it's fantastic if you can give education online to loads of people, but let's not forget about the teachers, right? And making sure that there's a need to train teachers, and that face-to-face interaction is important. If you're working on traffic flow, it's important to not only enable, better flow of traffic now, but also consider, what are the consequences of this on, the local atmosphere in terms of pollution, and are there solutions that we should be thinking about for more efficiently moving large numbers of people around, right? So I really encourage, again, people to think about those big problems. Oftentimes, we want to go for the bite-sized problem because we can actually solve it, and we should, right? There are lots of problems we need to solve now, but let's also think about those future changes. So I'm just going to close with one of my favorite quotes. With great power comes great responsibility. Let's do awesome things. Thank you. Questions?
Hey, thanks for the great talk. I'm wondering how your approach changes for communicable diseases as opposed to non-communicable ones. So infectious, non-infectious diseases, and how you would anticipate a change in your modeling.
I don't think that the methods would change. So we're not doing any network analysis related to the communicable diseases. So even when we're talking about something like HIV, we're not other people do a lot of work on trying to figure out what are the networks and the spread and such like this. We're just focusing on the treatment of an individual. So I don't think our treatment our stuff would change significantly. I think this could be. We're kind of limited just by the manpower, right? We build relationships with our clinicians, and we really work closely with them. So we focus on HIV and critical care for this sort of work. But I would imagine, diabetes, TB, any disease that requires many decisions, basically, this sort of framework should follow.
Hi. A couple of questions. So when you spoke about random policy, no action policy, and the learned policy doing the same thing, so the no action one was explained, and it was pretty clear because you said that, for example, for 100 hours, there won't be so much actions, and the policy learned that. But I still don't understand why the random policy behaves the same.
Why you got good solutions for the... So what was happening in all of those cases is that the thing that wasn't shown on the plots is the density of where the data lie. And so, because I was only showing the difference between the clinician and the agent, but I wasn't showing you the actual values of the clinician and the agent. So a lot of the clinician data, basically all of the data are kind of clumped toward the middle. And you have very little data toward the side, which is also why you get just lots of variance in those regions.
Okay.
Yeah.
And maybe a couple of slides before that, you introduced DQN and LSTM, and you said that sometimes it was having some crazy recommendations, so you blocked the rare actions. And I was thinking, how do you proceed to do that? Because I guess you will always have some patients that would need those rare actions. So how do you actually proceed?
Right. So, and this, I think there's this kind of raises a question of how a system should interact with a clinician. I would say that I'm fairly confident whenever we filtered things, they were bugs. It's not. Again, you know too much about how the sausage gets made in terms of like optimizing neural networks. You're pretty sure that it's you that was wrong. But I think that if we presented the option, one thing we're doing now is we're analyzing the results of a user study. This is in the psychiatry space of the effect of how we present an explanation and what the clinician does in response to it. And the goal really would be how to figure out to present something in a way that the clinician feels good about overriding it when necessary, if they have that special knowledge about that patient. In the psychiatry space, it might be that I don't recommend this drug because it's an activating drug and the patient has insomnia. But maybe the clinician's like, no, I'm going to give them a sleep med and it'll be fine, or something like that. There you go. All right, well, thank you again.
Thank you very much, Finale, for that very insightful talk, and I hope it's inspired many of you who are tackling healthcare problems in Africa. Can we update the slides at the back, please? Okay, so I think we have a little bit of technical difficulty, but never mind. We just wanted to take a few minutes now to recognize and celebrate the extremely hard work done by our practicals committee and tutors this year. So I know many of you attended the practical sessions during the week, and I hope you, to those people who attended the Indaba in previous years, I hope you just see that there's been a very steady upward trajectory in the quality of those practicals. And this year, in a very large part, that's due to our fantastic two head tutors, Taliesin and James. So I'd like to invite both of them on stage right now to just collect a small token of our appreciation for all their hard work.
I think this goes without saying, but of course, Tali and I wouldn't have been able to do this without all our head tutors and all the other tutors who gave us tons of feedback and put in a lot of hard work during the practicals. So can we get all of the tutors to come up on stage quickly so that everyone can see who you are, and we'll get another round of applause going. Yeah, let's just have everyone file up in front of the screen, and then we'll get a photo or something, I guess. Yeah, of course, a special thanks to all the head tutors who were sort of managing things in the labs and who were people who put in a lot of extra effort to give us feedback. So to all the head tutors, a special round of applause. Let's give it to them now quickly. And especially we need to give thanks to Seb, who wrote the RL prac, so another round of applause for him. Thanks, everyone.
Okay, so just before the break, just a few announcements. So some people, I believe we still need to collect some money for accommodation. So if this is you, please meet Elizabeth outside. So buses for the closing event, which will take place at the Safari Park Hotel, are going to leave around, I think the first bus is around 6:20. Also in the parking lot here. So if you make your way there after the final session of the day to get on the buses, we'll have drinks coupons available for you. And these will be, each person will get 3 coupons for drinks at the event. So please make sure you collect these as you get into the bus so you can get your drinks at the event. We'll also have some swag from some of our sponsors available, which you can pick up on the way to the bus. No need to rush, there's enough for everybody. There'll be a lost and found box in front. Anyone who's staying at Nyayo, you can have your breakfast at KUCC tomorrow. And finally, reminder to use the Slack channel to coordinate airport transfers and share Ubers and that kind of thing. Okay, so enjoy your break, and we'll see you again later.